First of all right. Welcome everyone. So this is going to be a brief and short introduction to DeepRL. So just so that everyone knows, it's pretty, this whole area is a very large area, and it's sort of like impossible to actually uh, go through all of the details in a single lecture. So what I want to try to do over here is to give you more of an intuition and an introduction into this field, so that if you're interested in it, then you can sort of start learning more about it. And also, since it's an introduction, feel free to like interrupt and like ask questions. There are three modes of asking questions. You can either post it in chat, in the Q&A box, or raise your hand. And all three ways are fine on the Zoom interface. All right, so let's get started. So before we start, just to give you some introduction into what my research is and why I am interested in DeepRL. So most of my work, it focuses on robotics. So over here you can see an example of robots interacting with objects on the top left. On the top right, you can see how a drone is sort of learning how to fly in this like unseen environment. On the bottom left, you should be able to see a robot which is trying to unfold a cloth. And then on the bottom right, you should see a video of these like cheap, low-cost robots which are just interacting in people's homes and trying to do some silly things and pick objects up in these homes. So one of the reasons that I am interested in reinforcement learning is because in order to solve these type of problems, in robotics especially, RL has recently shown to be a really powerful tool. And this is like one of the reasons why we are so interested in learning more about it and actually creating more RL algorithms to help us solve problems of these sort. All right, so now let's actually get started. So part one is more of motivation and introduction. So a lot of you might have already heard about DeepRL, and I'll go through a few of the prominent works in DeepRL which has generated a lot of excitement. So one of the first works which actually got a lot of news press and sort of excitement was this work from DeepMind, where they showed that with a single algorithm, you could train an agent, or you could train a model to solve Atari games, all the Atari games in the Atari suite. And so here's an example of the model which is running on the left. And then after this work, so this work, it came out in 2015. And the next year, what they were able to show is that you can actually use these type of techniques to actually solve much harder problems as well. So this is the game of AlphaGo. And one of the sort of fundamental challenges in AlphaGo was that the amount of possible states in this game is more than the number of atoms in the universe. So explicitly searching for the future is just not a feasible option over here. You have to do some sort of learning. And in 2016, what they were able to show is you could create RL algorithms that could even beat the best humans at this game. Now, this is an example of a more complex game in some sense, where you have to have some sort of teamwork as well. So this is the Dota game, which OpenAI showed that you could again train a DeepRL agent, which could again beat some of the world's best players. Now, apart from games, as I've also alluded to a little earlier, you can use these type of DeepRL methods on robots as well. So here, what you're seeing is a robot which is learning how to open doors just through deep reinforcement learning. And over here, what you're able to see is after around 2.5 hours of training, it's able to figure out how to open these doors. So more recently, what we're seeing is algorithms in DeepRL are also being used for like other fields as well. So over here on the left, you can see a new paper on how to use RL for advertisements. And on the right, you can see how people are trying to use RL for trading stocks as well. So one sort of high level thing which you should all take away from this is that this sort of area of RL, it can be used for a lot of different problems, from how to solve games to how to make robots do interesting things to things like advertisements and even stock trading. Okay, so a lot of you might also have a question about why RL? What is so special about reinforcement learning that you have not sort of already learned about in the previous lectures? So in these next few slides, what I want to sort of share with you is some sort of intuition of why is RL actually necessary? Why do we need this? Okay, so let's say you are a self-driving car. So you're a car on the road and you need to figure out how to drive. And let's say all that you're equipped with is a camera. So this is an example of an image that this agent or the car is able to see. Now, in order to drive in a successful way, you'll have to understand what is in this image, right? And using supervised learning, you can actually go a long way. So let's say you want to ask a question of how do you classify what is in this image? Now, this is actually a solved problem. So if you have X, which is an input, so you just use this whole image as an input, and Y is your class labels. Things like, is there a car? Is there a person? Is there a street? Is there a road? And if you frame this problem as a classification problem, it's very easy to solve it. So if you just go to this Clarifai website, you can feed this image as input, and you'll automatically see that it's able to see that there's a person, there's a car, and there's a street. All right. So this is already a lot of information that you can get from supervised learning. Now, apart from classification, you can also do things like generating a caption. So again, this is a supervised learning problem. You feed an image into a network, and then the network can output a sentence of what it sees in this image. So one sample output that you could get is something like pedestrian crossing a road, which again is a lot of information about the scene. And again, you can sort of learn these models just by doing a supervised learning framework. You can do even more. So you can also run a detection algorithm where it not only tells you what is in the image, but it also tells you where are things in the image. So it can tell you where all the humans are, where all the cars are. And this is, again, useful information if you're a self-driving car. But if you look at all of these problems, none of these actually answer what you really care about if you're a self-driving car. And that is, where should I go next, right? If you're a self-driving car, the main thing that you care about is how should I steer the wheel, or how should I apply the acceleration? And none of these other methods actually tell you what is this action that you need to apply. So this type of problem is also called a sequential decision-making problem. And you'll sort of also see that a lot of problems can be cast in this way. So what does this mean? This is a lot of words to unpack. So the first word is decision. So over here, you can think about what sort of actions is your car able to apply. So it can go in front, maybe go left, or go right. And so these are all possible actions that your car can apply at any point of time. The next word which we want to sort of unpack is sequential. So what's actually happening in this problem is that once you apply an action, you will see a new observation from your environment. So let's say if you decide to go straight. Now, if you go straight, you'll go closer to this person who's trying to cross the street. and you may hit this person. So you'll see an observation of your car about to hit this person. If you go left, you might hit the car which is on the other lane. And again, you will see the next observation, and you'll probably have to make a new action of, again, if you want to go left, right, or straight. So what you're having in this problem is that when you're making a decision, you're not just making a decision which is good for this particular instance of time. You have to make a decision which is going to be good for the future as well. So maybe if your goal is to just go as fast as possible, you may think that, oh, I'll just keep going straight, and so I'll just keep applying the action of going straight. But if you do this, you may hit a person, and if you hit a person, you may have to stop. So in the long run, going straight right now is probably not the best thing to do. In this case, I guess what the agent should do is either brake or to maybe swerve right and try to avoid this pedestrian who's trying to cross the road. Okay, so in sort of more math terms, what you're having over here is you see an initial observation, which is x0, which you see over here on the left. And then from this observation, your self-driving vehicle will produce an action. Let's say it's y0. So this is the action of either going straight, left, or right. Now, based on this action, what happens is that this action will affect what you see next. So x1 is the next observation. So if you go left again, you'll probably hit the car. So x1 is sort of an image. You can think of it as an image where your vehicle is just about to hit this other vehicle. And then again, from this observation, you can output what the next action needs to be. That is y1. And this thing, it keeps going on, until you're able to solve the task, or until someone stops your car. All right. Any questions until this point on this high level of what's happening?
There's two questions in the Q&A. Do you see them, or do you want me to read them off to you?
Let me actually open them. Okay.
I can read them to you if you want, whatever works best for you.
Yeah, I've just opened it. So initially I had the chat box open, but I'll just switch it out with the Q&A. All right. So Sebastian has asked, in the DOTA example, which information the algorithm receives and what does it give back? Can he only see the screen and hear the audio? Yeah, so this is actually a very good question. So the information that the algorithm sees is not an image, because processing images are usually hard. So what they do over here is they have a sort of lower dimensional state of the world. So for each character, they're able to sort of have information of what the nearby characters are and some information about the terrain. And that is what's actually it as input into the algorithm. So it's not full information. So it doesn't get to see everything, but it gets to see some sort of local information around the character. It's not exactly what a human is seeing as well, because a human has to look at an image and process what's happening in the image. But for the algorithm just gets the raw state of the environment. Okay, so there's a question about Ali, which I'll leave for the end of the talk. Okay, then there's a question by Jean-Luc on what type of sensor fusion are you applying for making those decisions? Okay, so in this case over here, we're not looking at any specific form of sensor fusion. You could do sensor fusion, or you could also not do sensor fusion. So let's say you only had a single camera, right? And then you don't have any other sensors. So in that case, you don't have to do sensor fusion. What I'm sort of going over here is a very general framework. So you could do a sensor fusion, or you could also not do it. But whatever information you have, you can sort of just group all of that information into this X0. So you can think of this X0 having all of your sensor information baked into there. All right, so let's keep going. Okay, so why are we interested in RL? So There are three main reasons. The first reason is that RL, it gives us a framework to actually solving these types of sequential decision-making problems. And so since it's providing us a framework to do this, you can actually use it for solving multiple forms of these problems. The next thing is that it RL is compatible with with these expressive deep networks. And algorithms which actually use a deep network along with RL are often called deep RL algorithms. So you can also do RL without a deep network, and that's just called standard RL. But if you use a deep network along with RL, you call that a deep RL algorithm. And the third thing, which I think is probably one of the most important aspects, is that since you are having a deep network embedded inside this RL algorithm, what it gives you is the ability to learn from large-scale data and experience. And so just how you have seen in the past lectures, how you can use a deep network and use it to sort of learn from large amounts of data, you can do the same thing in RL. But instead of having a lot of just static data, you can think about having a lot of interactions with an environment. So in the case of a car, if you had a simulator of this car going around, you can actually learn a deep RL algorithm on that experience in the simulator. Okay, so let's try to also go over a few preliminaries in RL, so it makes it a little bit easier to understand what's going to come next. So in the standard framework of RL, so it's shown on the left over here. So there are two main objects in some sense. There's the agent, and then is the environment. So what the agent is doing, so you can think of your agent as your robot. So in the case of the self-driving example, you can think of this agent as this self-driving vehicle who's trying to move around on the street. The environment over here, you can think of the environment as the physics of this world, right? So if you're applying the throttle, there's something which makes this car move in front. You can think of that as the environment. So you have this agent, you have this environment. The interactions of this agent and the environment are sort of predefined in some sense. So the agent applies actions on the environment. So the steering is an example of an action. Applying the accelerator is an example of the action. And so once the agent applies actions on the environment then gives the agent observations. So observations are either visual information of what it's seeing, or state information of what it's seeing, or any sort of information of what has happened in the environment. Now, along with observations, the environment also gives the agent something which is called a reward. So what a reward is some notion of success or failure. So if the agent is doing something which is good, you give it high reward. If the agent is doing something which is not as good, for instance, like hitting a car or hitting a pedestrian, you give it a negative reward. And so the goal of this agent now is to apply actions in the environment such that it gets the maximal reward in its lifetime. And so the goal of this agent now is it's going to see observations from your environment, and then it's going to apply actions such that it gets better and better rewards from this environment. So again, if we were trying to maximize the rewards in the case of the self-driving car, it would learn to sort of avoid the human and avoid the car, and sort of go on the street while following all the rules and not hitting anything. So if you were successful in training an RL agent of this sort, you would expect this vehicle to sort of be a good vehicle and drive well on the street. Now you can use the same framework in a bunch of other problems as well. So let's say you wanted to have a robot that could solve a Rubik's Cube. So in this case, you can think of your agent as maybe a pair of robot hands which can move around. The actions would be maybe the force and the torques that that the hand can apply on the cube. The environment over here is the Rubik's cube and the physics of how the sides of this Rubik's cube actually move. The observations are probably visual observations of what the robot is able to see, and the rewards, it can be something as simple as a +1 if the Rubik's cube is solved, a -1 if the Rubik's cube is not solved. And now you can actually train an agent to solve this Rubik's cube, and hopefully, if your RL algorithm works well, your agent should learn how to solve this Rubik's cube. Another example is the example of Go. So over here, your agent is a player now instead of just trying to solve a task. Now you have this sort of competitive environment, and so you can think of your agent as one of the players of Go. The actions are moves that this agent can play on this Go board. The environment is just rules of Go. So based on the move you make, how the board moves, you can sort of think of that as the environment. Observations, you can think of observation as an image of this Go board, or maybe even the locations of every piece on this Go board. And the reward over here, it can be, if your agent wins, it's a +1. If your agent loses, it's a -1. All right, so you can use this idea of having this agent, environment, action, observations, and rewards for a bunch of other problems as well. So here I'm going to list a few other problems over here. And at this point, I can also take more questions. So as people are thinking about this and writing questions, I'll go over this list. So these are all examples of problems that RL was successful in solving in the past. So the first one over here is flying stunt maneuvers in a helicopter. So over here, you can give a positive reward if your helicopter is following what the trajectory is, and a negative reward if your helicopter has a crash. Okay, so there's a question from an anonymous attendee. Is the agent's goal to maximize reward at each action, or to maximize the total reward from all actions? So in the usual framework, what we do is we want to maximize it from, it's called a cumulative reward maximization. So you want to maximize a total reward from a bunch of different actions in a temporal sense. So you can say something like, I want to maximize the reward an agent gets in 1 hour, in a 1 hour amount of time. And so the goal for this agent is to be able to solve the task as well as it can in this 1 hour amount of time. You usually don't want to make it infinity, because then it can just be really, really bad and say that, okay, maybe in the future at infinity, I'll do something good. But so you want to usually keep like a fixed horizon in which you're measuring how good your agent is.
I have a question in the Q&A.
Yeah, so I just answered that question.
Oh, I'm so sorry. I stepped away from it.
Yeah, let me just hit the answer live button. So, all right. All right, so then there are like a few other problems over here. I'll just leave it in the slides and you can probably read about it later as well. Okay, so what makes RL sort of a fundamentally harder problem than just normal supervised learning? There are actually two main things over here. So the first issue is that the examples of the data that your algorithm is seeing is not IID. Now, what does it mean by being IID? In supervised learning, when you start off, you start off with a data set. So this capital T over here is your data set. So let's say you want to do image classification, you can think of ImageNet as your data set. And so if you're doing a supervised learning algorithm, you just have a static data set. You're going to sample examples from this data set and then learn a model which can output the Y from the X, right? And so what's happening over here is that this sampling procedure of the data is independent of how good your model is. Let's say you had a neural network which was just really bad. That network being bad, it does not affect the examples it's seeing during training, right? Because the whole sampling over here is just purely based on the data set. It's completely independent of that model itself. Now, in reinforcement learning, on the other hand, because you have this sequential nature, what's happening is that the actions you apply affects what you see next, right? So let's say if you were a self-driving car and you always chose to go left, right? So let's imagine you have a really bad algorithm and you have a really bad model, and it says, okay, I'm always going to go left. And now what's going to happen is that all the future examples that you see are going to be examples of your car hitting into another car. You will never see an example where your car is just on the freeway, just going without hitting anything. And so what's happening over here in RL is that you have a correlation between the outputs of your model and the data it sees during training. And so it's like a chicken and egg sort of problem over here, that if your model is not working well, you see really bad examples. And if you see really bad examples in training time, you're not able to train your model well again. So this is one of the fundamental issues when you're trying to solve an RL problem. Okay, the next issue is that ground truth actions are often not available. So what does this really mean? So in supervised learning, the output is known. So if you have X as input, you usually know what the Y is. So let's say you were trying to solve an image classification problem again. You have this data set like an ImageNet, which was created by asking humans to actually label, is there a cat in this image? Is there a dog in this image? And so there was a human which saw the image and said, okay, this is what the output needs to be. And so when you're learning a supervised learning problem over here, you know exactly as you're training what the output needs to be. On reinforcement learning, on the other hand, you do not really know what the ground truth action or what the true optimal action needs to be. And just to give you some intuition of this, let's say you have to solve a Rubik's Cube and you see the state of the Rubik's Cube, let's say it's exactly how this person is holding it. And let's say I show you how to move the Rubik's Cube. But just by observing that, you cannot say how much force was applied on this Rubik's Cube, right? Because you cannot query into the action, into the torques, for instance, of what this human was sort of applying on this Rubik's Cube. And so in a general case in RL, it's very hard to obtain these ground truth actions from humans. Now, of course, there are a bunch of cases which we'll also see over here where you can obtain these ground truth actions, but in general, it's very hard to actually obtain these ground truth actions. Okay, so this is the second fundamental challenge over here, where it is very hard to actually get the true actions that you want your model to output. All right, any questions up to this point? All right, so now we'll go into why is deep RL happening right now. So if you look back at a little bit of history, reinforcement learning algorithms have been used to solve interesting problems since the early 1990s. So here on the top right, you can see an example of how RL was used to solve the common game and do sort of as well as humans or even better than them. And on the right-hand side, you can see a paper on how people have used RL to actually make robots learn. And again, this was done in 1993. So this is so RL has been used for a long time, and it sort of, in some sense, it reflects how even supervised learning, it used to be done a long time ago, right? So this is again work from LaCoon in the 1990s, and these networks existed in the 90s as well. But what happened, like in the last 5 to 10 years, is that we have seen the sort of emergence of these really deep networks now, multiple, like a lot of layers in these networks. And there are actually 3 main reasons for this, right? In supervised learning, at least. The first reason is that you had these really powerful GPUs which could process a lot of information. Then we were able to create really smart algorithms that could actually build on top of these earlier networks. And then finally, we had access to this large scale information, this large scale data sets like ImageNet. Now, in RL as well, I've already shown this diagram of how this agent interacts with an environment. But now you can also sort of use all of the things which you have seen in supervised learning in RL. And so what this means over here is that instead of this agent, you can use a neural network now. So you can think of a neural network, which is now using observations as input and outputting actions as output. And once you use a neural network here, you can get all the benefits that we have seen in supervised learning now into RL. So again, we're able to use, in RL, we're able to use these really powerful GPUs. We're able to create really smart algorithms. And then for experience and data, what we're able to do is we're able to create a simulation of the world and get a lot of experience from those simulations. Okay, so now we'll go into part 2 of this lecture, which is going to be how do you learn behaviors by doing just supervised learning. So in some sense, you can think about this part as how do you do a decision making or how do you solve a decision making problem without using any rewards. Okay, so again, before we start over here, let's go through some of the usual terminology. So in this case, I think what's happening here is that there's an animal. So it's a tiger, and you have just, you're like walking in a jungle and you just saw the tiger, and now you have to make sure that you're not eaten by this tiger. And so the observations that you see, so you have eyes, so you can see this tiger, and so the observations that you see, we usually call this OT over here. And then after seeing these observations, you then you feed this observation into a neural network or into your brain, and then you output an action, which is AT. So AT, it denotes the action that they're going to apply. In this case, you can sort of think of the action as, okay, run left or run right. And so in a general case, this procedure of applying an action, you can think of it as a stochastic process. So that's why you'll see that the way we are sort of denoting this model is a stochastic process. So given an observation, you will output a distribution of possible actions. Now this thing or this model which is outputting these actions is called a policy. So it's a decision-making policy. You can think of it as the strategy making sort of masterpiece of this algorithm, where it feeds in, where it takes as input some observations, and then it outputs what the right strategy to do over here is. Okay, so OT is an observation, AT is the action. Then you can build a policy where you use OT as input, use observations as input, and then your output actions, which is AT. Now this eta over here, you can the eta over here is just all the parameters inside your network. It's all the learnable weights inside this network. Now there's another aspect over here which we usually just sort of not go into a lot of detail, and that's what the state is. So when you usually have an agent which is inside an environment, you are not able to observe all the information in that environment, right? Like, so for instance, if you see a tiger, you're not able to say exactly what's the pose of this tiger, right? You know that there is a tiger, but you're not sure exactly how far it is. It may be maybe 5 meters away. It could be like 5.1 meters away. You may not be sure about exactly what the state of the tiger is, but you have a lot of information about the tiger. And so HT is usually the lowest dimensional representation of your environment. And if you're able to obtain this, you can actually do RL much better. But in the general case, it's hard to obtain this true state of the environment. So here's again another illustration of this. So let's say you have a deer over here and a cheetah. The observation, it can be an image of this whole scene, whereas the state, it would just be these sort of 2 frames, one on the cheetah and one on the deer. Right. There's a question. What are some internal conflicts that are encountered when pursuing what is the best decision to make when making a certain observation? So here, a lot of these models are sort of feed-forward models, right? So it takes an observation as input, and then it goes through a bunch of these layers, and then you see the action as an output. So all of the internal conflicts is all internalized in this model in some sense. So once it learns how to output actions, it's usually hard to see exactly what the network is doing. And this is sort of an open area in research as well, where you want to where the goal is to sort of get more interpretable understanding into these networks. But in general, it's hard to say how these internal conflicts have been sort of internalized into this model. But this is a very interesting question, and I think there's a lot of research happening right now to actually to sort of give us more information about these internal conflicts. Okay, so now just sort of like understand exactly how this process is going. So at some time step, let's call this at time step equal to 1, you see an observation O1. You run this observation through your policy I data, and you get an action as output A1. Now, based on your state and your action, both of these will then determine what happens next. So this thing over here, you can think of this as your environment, where based on based on the state of the environment at one time step and the action that your agent is applying at that time step, it determines which state will you end up next. So if you go straight to the cheetah or to the tiger, it may start attacking you, and that's probably what the next state is going to be. And again, this is a stochastic model over here because the environment is stochastic. Maybe this tiger has probably already eaten, and it doesn't want to come and attack you. So there's usually going to be a distribution over what do you see next. And then after you move into your next state, which is a time step equal to 2, you then have the observation. Then from the observation, you use the same policy to output what the next action is, A2. And then again, based on S2 and A2, your environment will take you to the next time step, which is S3. And so this keeps going on and on, right? Because you can keep applying this policy over and over again until you survive. So another sort of quick note over here is, so over here we're sort of assuming that for any ST is dependent only on ST minus 1 and AT minus 1. So this is called the Markov independence property of the system. And so it means that the history of what happened in the past, it doesn't really matter. What really matters is only the previous state, right? So in the determination of what happens at S3, whatever happened before S2, it doesn't really matter. All the information about the environment is condensed into only S2. Okay, so let's keep going on. Okay, so now to actually train this model, one of the most straightforward way of training these sort of policies is through imitation. And so this is like a video I like to show about imitation. So here is an example of a baby who is watching Rocky on TV, and you're able to see how well this small baby is able to imitate what Rocky is doing. And what I want to sort of drive home over here is that we as humans have this natural ability to see things and imitate them. And there have been a lot of algorithms which try to use this fact. So if you're able to sort of obtain human information of how to solve a problem, you can actually use that information and train a policy to imitate that information. All right, so let's look at a case study over here of self-driving. So over here, again, you have a car, you have an image that your car is able to see. And then you want this vehicle to output an action, AT, which can make this car go straight on the highway and not crash anywhere. And so the way we're going to do this over here is that we're going to collect a data set where we have a human. So we're going to have a human who's going to drive the car. We're going to observe what the human is doing. So we're going to see what observations the human is seeing, and then what actions the human is applying. We're going to use all of this data and keep it in a training in a data set. And then we're just going to do normal supervised learning on this data set. So we're just going to try to predict actions AT from observations or inputs OT. So this way of sort of learning a policy is also called behavior cloning, because you're trying to clone the strategy of this human. Okay, so now I'm going to play for you a video of one of NVIDIA's work over here. All right, so what you saw over there was a car which was able to drive by itself only using a neural network. And that neural network was trained in this behavior cloning fashion. So how it actually trains is that, so this is like a small a graphic of how it trains. So let's say you have a car over here. This car actually has 3 cameras on it. It has a camera on the left, it has a camera pointing straight in front, and then a camera on the right. Then from the examples that you see from the human, which is on the top over here, so we are able to record what a human was able to do as they were driving. And then we are going to train a CNN or a neural network over here, which is going to take all of this information of the left camera, the center camera, and the right camera as input. And it's going to try to output what the action or the steering command needs to be. Then we just measure what the steering of the CNN is versus what the steering of the human is, and then just apply a back propagation to adjust the weights of the CNN so that the network is able to match what the human was doing behind the wheel. So it's a pretty straightforward algorithm. And as you have seen in the video, you're actually able to make a car drive on the road using it. Okay, so there's a question from Sophia on in an unlikely accident / event, how does the self-driving AI able to react to something it wasn't trained on? So this is actually a very it's a very important question, and oftentimes if your car hasn't seen something it has been trained on, it usually will not work that well there. And so that's why for a lot of self-driving vehicles right now, you usually have a human in the loop. So you either have a human at the driver's seat, sort of just like about to make sure that, you know, if the car does, if the car is going to do something weird, they can actually hold the steering wheel and sort of unsteer it in the right way. And so it's very hard for algorithms of this sort to actually work well in an environment it was not trained on. Yeah, and so you usually need a human in the loop to actually make sure it does not crash. Okay, so another example I want to show over here is a self-flying example. So in this video, what you're seeing is observations from a drone. So a drone was again trained in this sort of behavior cloning manner, and it was trained to sort of go in a forest and not hit trees. And so over here, what you're able to see is how this drone is able to fly through this forest without hitting these trees. Okay, so any questions up to this part? We're about to go into part 3, which is learning with rewards, which is basically if there's no expert information, if you do not know what the ground truth actions are, how do you use RL over here? Okay, so there's a question from about for the self-flying drone, how applicable are the SLAM SDK algorithms for mapping and localization, basically doing odometry and trajectory analysis. So in the example which I just showed right now, they are not doing SLAM or like anything of this sort. So SLAM and those line of algorithms which you mentioned is really important if you want to do long range planning, right? So if you want to go from, let's say, here to the airport, for instance, you know, you can use SLAM for that. But what you're using it over here is to do this sort of like maneuvering, which is very close to the obstacles. And so oftentimes what's happening over here is that you want to create algorithms which can run at a very high frequency. And so if you do these type of trajectory analysis, when you have to make a decision in a split second, it's not going to work as well. And so having a learned model works really well when you have to make a split second sort of action of whether you should go straight or go left to evade a tree or to avoid a tree. Okay, so now let's look at how can we actually learn from rewards. So your environment is, as your agent is interacting with the environment gives the agent some notion of success, right? And this notion of success is called a reward. So if it gives you high reward, it means that you're doing something good. If it's giving you low reward, it means that you're doing something which is not good and you should try to avoid that. And the goal for this agent is to maximize the rewards it sees during its lifetime. So one really popular algorithm is the deep queue network. So I've already shown you this video before, and we'll sort of go over how this algorithm actually works. So the method is called, or the sort of architecture, or the model is called a deep queue network. And so you may know what few of these words mean. So when we say deep, we just mean that we're going to use a deep network, like a deep architecture over here with like multiple layers in it. And so you know what a deep network is, but what you may not know is what queue is. Right? Like, what is this word queue over here? So first, let's go over what exactly queue is. Okay, so queue is also called the state action value. And what this means is it's a function, basically. So it's a function which you input the state and action into this function. So you input HT and AT. And what it gives you is the expected value of taking the action AT at a state ST. So what does value mean? It means that what is the reward that you can expect to get in the future if you start at state ST and apply the action AT. So let me just go over that again, and in the form of this math equation over here. So what you're doing is that given that you start at some state ST, so let's say you're at this state ST over here, and there are multiple possible actions that you can take. Let's say you can go straight, you can go left, or you can go right. So this is your options for AT. What Q is going to tell you is that the state that you end up with, right? Because you're going to go to, like, so you can have three possible futures over here. It's telling you how good is this state over here. This state versus this state versus this state. And so intuitively, what it means is that you want to go to, you want to choose actions, you want to choose these actions AT such that you have high value, such that you have this high Q value at those next states. And so in terms of the in terms of what is inside the expectation, you see this RT plus 1, RT plus 2, and RT plus 3. So these R's are the rewards. So RT plus 1 is the reward that you see in the next time step. So it's the reward that you see over here. So this is RT plus 1. RT plus 2 is what is the reward that you would see from the next state. Because even once you reach here, you're then going to apply a next action, you want to apply a next action, you want to apply the next action, right? And so it's sort of like, it's sort of adding up all the future rewards that you could get and applying them into the single thing, which is called the Q value. So it's sort of like an aggregation like operator, where it's aggregating everything that you want to see in the future into this single output at that state action pair. Now you will also see that there's a gamma term over here, and you may ask, why is there this like gamma term here? So this value or this gamma term is usually between 0 and 1. And what it is used to do, it's used to discount the future rewards. So what this means is that you want to have higher value for a reward that you get right now, rather than a reward that you get in the future. So it's a way to sort of trade off whether you care more about having a reward right now or getting a higher reward later on in the future. So if gamma is equal to 1, it means that it doesn't really matter when you get the reward as long as you actually get the reward. If gamma is equal to 0, it will just mean that I care about the reward that I get only at this point of time, and I don't care about anything into the future. Okay, so there's a question. Does it take a mean of the future rewards or a maximum or something else? So it is the sum. So it's not the mean, it's the sum. So over here, it's a reward that you see at one time step plus gamma times the next time step plus gamma squared, the one after that, plus all the way up to infinity. But now, if you know that, so this is like a little bit of math over here. So if you know that your rewards, let's say RT, is between 0 and some R max. So let's say there's like a maximum amount of reward you can get at a time step. And if gamma is less than 1, I mean, it can be a homework for you to solve, but you can sort of show that this expectation over here, this expectation is bounded. And so what it means is that this expectation will always be less than some value, some Q max value. You can sort of use this as a homework to actually show what this Q max value is. So there's a maximum that you can possibly get, but then of course you will not be able to always obtain that maximum because it means that you have to get R max at every time step, which is going to be really hard. All right. Any more questions over here? Okay, so you may not have understood exactly what's happening over here, but the sort of high level intuition to sort of take away from here is that the Q is some way of aggregating information about the future, but at that initial time step. So it's aggregating what you see from T to infinity into what you see at T over here, at the time step T. Okay, so what does this actually give you? Why are we introducing the sort of complex Q function over here? So the reason we are doing it is that once you have the Q, there are some really nice math on top of the Q. So there's like a bunch of equations called the Elman equations. And one of the equation is of this form. And so what it's saying over here is that once you have solved the problem, that is, once you have the optimal Q function or the optimal policy of how to work in this environment, the optimal Q has a self, like a relation with itself. And so what it's saying is that the optimal Q value at some state S and some action at that state A is equal to the reward you see, the immediate reward you see after applying that action, plus gamma times the maximum Q you see at the next time step. Okay, so what does this mean intuitively? Let's say you're at some state S over here. You're applying some action A. This is S dash. So the Q associated with this state S over here, you can relate that Q with the Q associated with this new state and the best action. So this is A best. So it's like it's saying that if you know what the best action is at a certain state, you can sort of relate the Q of that with the previous Q. And so you have like this very interesting equation over here where you have the same function. So this is the same Q star, which is on the left side and on the right side. So you have an equation which is having a relation between Q both on the left and the right. Okay, so now how is this going to help you? So once you have this relation, what you can do is you can create an algorithm to actually learn this. So what you can do is you can sort of, so the first line and the second line might look like exactly the same thing. But what we're going to do over here is that instead of saying Q at optimal, we're now going to say Q at a specific iteration number. So let's say you want to start off with a Q network, which is completely randomly initialized. So let's say at I equal to 0, your Q is randomly initialized. What you can do is, since you know that Q has to follow this equation over here, you can repeatedly enforce this constraint on the Q. And so what you're going to say is that the Q you see at the next time step at I+1 has to relate with the Q that you see at the previous time step at I. All right. So now to sort of make this into neural network speak, or to or in machine learning speak, what we need is a loss function. And so what we do over here is we create a loss function now, where we're going to do supervised learning, but on the Q function. And so over here, we have the target, which is yi, and the output of the Q function, which is Q over here. And the target yi is just going to be this r plus gamma of the max of that same Q function. So this term is basically the same as this term here. And so you're just going to, you're going to create a loss, which is going to enforce a self consistency in this Q, in this Q function. Okay, so I won't go into the details of how exactly you train the model at this, but once you have this loss, and once you're able to train the model using this loss, you can actually learn a Q function which can solve these small games like the Atari games. Okay, the model that you use for Q is a deep Q network. So it's a deep network again. And so this is the exact architecture that they use in this paper, where they start off with a few convolution layers, and they follow that up with a bunch of fully connected layers. And at the end of it, you get the value for every action. So remember, you want to have the Q of state and action. So your state is basically the image as at input. So you can pick state or observation. So it can be observation as well. Then the action is going to be at your output. So in the case of the Atari games, each action corresponds with an action on the joystick. So on the joystick, you have all of these options that you see here on the right. And I think there are like 18 of these actions. And so each of these values is going to be the Q associated with that observation and this specific action. So this is going to be A0, for instance. Okay, so this is your Q network over here. You train this Q network using this OS over here at the bottom. And then you have this Q network, which is able to now solve these Atari games. Okay, so this work, it came out in 2015, and that's like 5 years ago, right? What you see, oh, so there's a question over here. Could you reiterate what theta represents in the loss function? Okay, so what theta is all of the weights in this network. So all of these all of the weights in these convolutions, for instance, you can think of that as a theta. All of these weights over here, which go in the fully connected network, all thetas are over here as well. So it's all the weights in the network which you're going to optimize. Okay, so yeah, so this came out in 2015, and that's like 5 years ago. So that's a long time ago, and a lot of things have happened since. So with this architecture, what they were able to show is for a bunch of the games, they were actually able to reach a performance higher than human level. So this line over here is the human level line, and what they have sort of shown over here is that at least in 2015 they were able to solve these games. I mean they're able to reach higher than a human level performance for like more than half of these games, right? But even at this time, there were still some games which were really hard to solve. So for instance, if you look at the worst games, there's this game called Montezuma's Avenge, which was really hard to solve. In fact, they got like a 0% performance on this game, which is like really low. And so there were of course these few games which were really hard to solve. And then over the last 5 years, they have created new algorithms that can solve these type of games also well. So just to give you an idea of what's happening right now, so there's this new work called Agent 57. If you see here, it came out in March 2020, so less than a year ago. And what they show in this work is that now you have an algorithm which can solve all of the games in the Atari suite. So all of the 57 games in the Atari suite, and RL agent can now solve it better than a human. All right, at this point, I can take questions. So again, another interesting thing over here is that, so you see this number over here. So 100% is equal to what the score an average human gets. So what this number usually means is that it's able to get better than like 47 times normal human. So it's not just like it's just going slightly above a human. It's like close to 47 times the performance of a human. All right, so I'll go to the last part of this lecture, which is again more of a intuition rather than sort of exactly learning how the algorithm works. And over here, we'll try to learn how to solve rule-based games. Okay, so this is the exact paper that we'll be going over. So here they learn how to solve the game of Go using a deep neural network and tree search.
There's a question in the Q&A box.
Oh, right. So the question is, what are the benefits of Q learning as opposed to other types of RL approaches? So there are a lot of RL approaches. Q learning is just one of these, is just one among a huge amount of RL approaches. The benefits of Q learning, I think like one of the it's one of the easiest ones to actually implement, I think, among all of the RL approaches. And since it's the easiest one to implement, it was one of the first algorithms which showed that using a deep network along with RL could actually show something very impressive. So I think that's one of the reasons why we actually covered that versus other RL approaches. The other sort of important thing to actually note over here is that for different sorts of problems, different RL approaches are the best approaches. So over here, this was like a game playing like example where you have a fixed number of actions. And so, you know, like if you have a joystick, you only have a fixed number of actions that you can apply. But let's say you had a continuous joystick where, you know, you could sort of have a continuous value of an action. Now, in those type of cases, Q learning, it doesn't work as well. There are a class of algorithms called policy, a policy gradient algorithm, and those work a lot better than Q-learning algorithms when you have a continuous action. So it depends upon the sort of RL problem that you're trying to tackle. Okay, so now let's go over this AlphaGo idea over here. Okay, so first of all, why is Go so hard for computers to play? So when you have a game, you can sort of represent a game as a tree. And so what this means is that you usually start from the initial state of your game. And then based on the moves you play, so let's say you can play like the sort of easiest move, you may go to the next state of the game. You can play a different move and reach here. You can play a different move, reach here, different move and reach here, right? And so every move you can sort of visualize it as a tree where you're starting off from like one node, and then each move, it takes you to a new future. And then in your new future, again, you can apply, the same, the same sort of idea again, where you can apply new moves and you again see multiple futures, and you can keep doing this over and over again. Now, let's say at every step you had B number of moves, and then you wanted to think about the number of the number of futures that you could reach after D steps. Let's say this is D over here. Then
there's two questions, one in the Q&A and then one in the chat.
Okay, let me go through the Q&A first. So the Q&A question is, at the point the model surpasses the human in the game, does it continue to grow exponentially, or is its main goal is to just perform better than its competition? So in the Atari game, there's no competition. It has a reward value, right? Like if you play the game, you get a score as you keep performing better and better in the game. And so its goal is to just keep getting a higher and higher reward. So it keeps playing until it gets a higher and higher reward. And then at some point, the sort of engineer who's training the algorithm says, okay, I've already expended all of the compute I've had, and so I'm going to stop the algorithm at this point. So you could train it for longer and it could get higher performance, but usually you stop it at some point when you're like, okay, it's fine. So
I was going to say the question in the Q&A is the same one in the chat, so it's fine. You posted it twice.
Okay. Yeah. So another thing, sort of note over here is these algorithms. The amount of data it sees is probably multiple orders of magnitude more than what a human sees when they are playing a game. Since it's a computer, it can actually simulate the frames of the Atari game much faster than what we as humans can actually do. And so it's able to sort of see a lot more frames than a human as well. So in that sense, it's not exactly a fair comparison, because you can start playing a new Atari game and maybe within like 1 or 2 tries, you can get a decent enough score on it. But these algorithms, they require maybe like millions of episodes on these games in order to sort of reach that really high performance. So it's not really an apple to apple comparison, since the amount of data the RL algorithm is seeing is not the same as what a human sees when they are learning to actually solve the Atari game. All right, so let's go back to the Go example. Okay, so so at every step of this tree, if you have a B number of options and you have a depth of D, what it means is that at the last step, so at the step of D, you have a total of B to the power of D options. Okay, how do you get this value? You can again sort of use this as a homework question. And so the complexity of the game tree is usually e to the power of d, which is huge, right? Because it means that if you just have to plan 5 to 10 steps into the future, because let's say you want to just plan 5 steps into the future, and you had maybe 20 uh, 20 possible moves you could make. It means that just for planning 5 steps into the future, you need 20 to the power of 5 possible futures, right? That is a huge amount. And so due to that, doing a brute force search is usually intractable because the search space is so huge. And so it is generally impossible for a computer to exactly evaluate who is winning, right? Because there are just so many options of what could happen in the future. Just going over every option one by one is just too large. Okay, so how do we solve this problem then? If you're not able to sort of go through every single option, how do humans actually go about solving this problem? So there are actually two main tricks that we as humans use. The first trick is that, okay, so this was this number, right? It was b to the power of d. So of course, we cannot do this full e to the power of d. So how do you make this large number smaller? So the first thing is that instead of going through a large depth, so let's say you're at this state, you can go here, you can keep going down through a large depth. So instead of doing a large depth, what we do is we reduce the depth by giving a value to the positions. So this is similar to the idea of the Q values, where you're going to aggregate the information of the future. This is the information of the future. You're going to aggregate this information of the future into a single value. And so if you're able to aggregate what's going to happen in the future, because you know that if you reach a certain state, the future is going to look good or the future is not going to look good, you can aggregate that information into the previous state. And so now what it means is that if you see a state which is not that great, you don't have to go and see what's going to happen in the future, right? Because you already know from your past experience that once you reach this state, it's bad. And so in this example, what's going to happen is that you're going to reduce your d to something smaller than d. So you're going to make your d smaller because you're going to have a smaller depth. So in that way, it can make this number smaller now because your effective depth is smaller. The next trick that we use is to reduce the branching.
There's a question in the QA.
Yeah, I'll go through that right after this question. So there's like a few slides after this which will sort of explain this answer, which sort of give you the answer for that question. Okay, so the second trick we do is to reduce the branching. And so what this means is that, let's say you're at a state here and there are, let's say, like 100 possible actions. Now, when we play games, we don't consider all moves equally. We automatically have a prior of what moves are good and what moves are bad, right? And how do we make this prior? We make this prior by sort of experience in the environment. As we play this game, we learn that, oh, if you play these moves, the future will not look that good. Or if you play these moves, you usually win. So we'll keep playing these moves over and over again. And so what we do here is, instead of having all of the options of moves that we can do at every time step, what we're going to do is we're going to now have a prior over which moves are good. And so by having this prior, what we're going to do is we're going to reduce the amount of branching, because we're not going to give equal consideration to all the moves, but have a high prior of only looking at certain moves versus looking at all the moves. Okay, so now once we reduce both this B and this D, the B to the D value, it becomes much smaller. It becomes much more manageable to actually search now. So now when you're searching, you don't search over all possible options. You only search over the options which have high value and which has a move which looks right in some sense. Okay, just to give a little bit more intuition of what's happening. So imagine this was the initial state of the game over here. Now you can sort of like see how after a few steps, this is not a lot of steps. This is just like, I think it's less than 10 steps away, right? And just by doing like around 10 steps, you already see that, it's like an exponential explosion in some sense. But if we are able to reduce the depth, you can now see that we don't have to go all the way into 10 steps. We can only just do maybe 3 to 4 steps. So now you have fewer number of options in the future. And then if you have a prior, now again, we're not going to choose every action. We're going to have a prior over which actions we want to search over. And this again, it reduces how many options we have to look at in the future. Okay, so there's a question on the Q&A. What exactly is the search target for the RL agent playing AlphaGo? So again, when you frame a problem as an RL problem, you have to create a reward function, right? So the reward function over here is the agent able to win the game or not? So it gets a reward of +1 if it wins the game. It gets a reward of -1 if it loses the game. So the way you train this model, let me actually show over here. It's a self-play learning algorithm. And so what it means is that the algorithm will play against another version of itself, a past version of itself. And so on either side of the board, it's basically two neural networks in some sense, playing against each other. And now when one neural network wins, it gets a high reward. And so when it gets a high reward, all the moves it did, it gets a high reward, right? And so when an agent wins, it's able to now build a good model of these values it gets at these states, and it builds a good model of what action it needs to take. These actions it needs to take. Right. There's another question. Does using reward and punishment values other than 1 and -1 have noticeable effects? For example, using +1 and -3. So it depends, but usually it does not. So in the usual case, what happens is that you normalize all the reward values. So let's say you had like a +1 and -3, and you then normalized it with max and min. It would end up just being a +1 and -1, right? And so if you're doing a normalization step, it just it does not have a huge effect really. Now, what usually matters, so this sort of the value of the reward matters a lot more if the reward is not a discrete thing, if it's a more continuous thing. But in the game, we don't have a continuous reward. You only have +1 if you win, -1 if you lose, right? There's nothing in between in some sense. But there are other cases in which there is an in between. Okay, another question, is the model built by the agent after winning the same as the policy? Let me try to unpack what this question means. So what's happening in self-play is that even though these two can be the same models, remember that these models are usually stochastic. So what does it mean by stochastic? It has a policy. So the data, it represents the weights in this network. It sees as input an observation, which is, you can think of an image of this Go board, and it outputs an action 80. Now this action is stochastic, right? And so even though it can be the same distribution, when the agent is playing the move, it may not be the exact same move. And so because of this, there is variations in this in the move, right? So like one like nice like intuition is that, let's say you have a normal distribution. So you can think of this as the output of the policy. Now, if I'm sampling from this, I could sample a sample over here, or I could sample a sample over here. Right. Now, maybe this sample, it wins, and so it gets a +1, and this sample, it loses and gets a -1. So then I know that this sample is more important. And so I will then update the weight such that this distribution looks more like this now. So it's more towards the sample which won rather than the sample that that lost. So I hope that sort of answers this question. All right, so here is how well AlphaGo actually does. So all of these methods over here, these methods are all sort of hand-tuned, heuristic-based AlphaGo, or hand-tuned heuristic-based Go solvers. And AlphaGo, it does much better than all of them. On the right-hand side over here, this is the sort of usual ranking of human players. So 9P is the highest sort of human grade that a human Go player can actually get. And through this thing, you can clearly see that AlphaGo is higher than the sort of best human. And this was actually shown in person as well. So there was a game between AlphaGo and Lee Sedol, who was the best Go player at that time, and DeepMind, the AlphaGo player, it won by 4:1, which showed that these algorithms can actually also beat the best humans at Go. All right, so we are nearing the end of our session. So I can take more questions now. In the slides, I've also linked a few resources over here if you want to learn more about RL. So again, RL is a very huge field. There's a lot of things to actually learn over here. There are like entire books on this field. And so there's always more to learn over here. And if you're interested, here are a few links to actually learn more about them. All right, so I'll take questions now. I don't know how much time we have for questions, but as much time as we have.
Like a minute, but yeah, you've been taking questions during your talk, so. There is the one pending question from earlier.
Oh, yes. So what are my thoughts on Ali? So I think it is really, really impressive, right? Like if you have played with it or seen the outputs, it's like really impressive. My question is really like, how does it work? And so I'm just waiting for the paper to actually come out so I can see how it works. And once you see how it works, it gives you a little bit more understanding of what it has learned and what it is not able to learn. It is clear that it is not learned like some levels of compositionality. So if you specify a scene in a certain way, it may not exactly line everything up exactly, but it does come really close. So yeah, so I don't have a lot of thoughts because I've not seen the paper yet, but maybe after I have seen the paper, I'll have more thoughts. All right, are there behavior cloning imitation problems where RL models could be trained on non-visual data? Yes, of course. So yeah, so you could use imitation learning for a lot of different problems, not just visual learning problems. Actually, in fact, even in the Go problem, what they do is, if you just start doing self-play from scratch, you have two agents which don't know anything about solving the game, and they don't do well at all. So what they did when they started out is that they first did a behavior cloning from human games, and then started doing self-play on top of it. And so even in that case, having the sort of pre-training phase with behavior cloning was really important.
Not that I was asked this question, I just want to add one thing.
Yes.
There was some recent cool work over the past few years where RL was used to learn syntax. So it like learned syntax of English sentences using RL without any supervision. So
yeah, that's really cool. Yeah, I feel like there are just like so many opportunities over here for like using all of these algorithms in new problems as well. Right. This question: if the network is better at predicting a certain occurrence compared to the human when driving, what parameters are there to enable the CNN to have primary control? So when humans are so there's this whole field of shared autonomy where you want to create systems where you have a human and a sort of artificial agent, and you want to sort of create methods which can seamlessly allow interaction between the human and this artificial agent, right? And so the way in which you allow a CNN to work versus a human, it depends on the shared autonomy system. So you can create a system where if the CNN says with like high confidence that yes, this is the right thing to do, and the human is like, I'm not sure, then it should go for the CNN, right? But if the human says, yeah, I am sure that this is the right thing to do, then ideally you should go to the human, even though if the CNN, it does not agree. You want to give the human sort of higher priority than a CNN, usually.
I think we're also now out of time, but that was really awesome. Thank you so much, Liorel. That was a really great introduction to RL, even for
Yeah, it was.
for like everyone, not just people who are full-on beginners in ML.
Yeah, thank you for having me. It was wonderful, also seeing these questions, because I think a lot of the questions are actually really hard problems in RL itself. So yeah.
Okay, I'm going to pause the recording.